Hello, in this video let's discuss fourth question of today's contest. You are given an integer n and undirected tree rooted at 0 with n nodes from 0 to n minus 1. This is represented by two linear edges of n minus 1 and u and v, indicates an edge between ui and vi undirected edge. You are also given an integer array nums where nums of I is the positive integer assigned to node I. Define value ti as the number of ancestors of node I such that v of I, nums of I into nums of ancestor is a perfect square. Return the sum of all t of I values for all nodes in the range I to n minus 1, which are all nodes in the tree. So n is up to 1 if I and numbers are also up to 1 if I. So the question is saying that we have to return the total number of pairs such that the present node and the ancestor node, the product is perfect square. So we have to return the total number of such pairs. So indirectly we have to find the total number of pairs in the tree such that they both are ancestors, like one is ancestor to other and the product is a perfect square. So let's for now let's forget about the tree and let's say we have an array. So we have an array and we have q queries or something. Let's say given an index I, we have to find the number of number of other indices where the product at that index and the product at this index, value of this index is a perfect square. For example, given index 2, we have to find the number of indices other than 2 such that v of 2 into v of that index is a perfect square. So what is the brute force? We can simply find an of n. We can traverse all the indices other than this, and if we try to find whether this is a perfect square, if it is yes, we can count, else no. So by of n we can find. But is there any other way where we can try to find the answer in less than of n? Maybe in off login or maybe in of 1. That is what we exactly want, right? So if we are unable to find an array, how can we find in tree? So firstly, we have to find some way in array so that given a number or index, we have to find the number of other indices or values which have product as perfect square with present value in off login or off one. So how can we do that? Before that, let's check the example. So 2 3, is it valid? No. 2 5 valid? No. 3 3, yes. 2 4, no. 2 8, yes. So 3 3 is yes and 2 8 is yes. So observe what are common in this, what are similarities in this for some time. So now in mathematical terms, what we want, let's say we have a. If we have a, we want some number like b square by a so that the product will be perfect square, which is b square. But here, this is exactly like brute force. So because given a, we have to find other value b also, such that only then we can find this, right? But this is also in division. For example, let's say we have a and we want something like a plus x. So if we want something like a plus x in of 1, we can very simply do by hashing because we can store all the values in map. And then if we know the x, we can find of 1. But here the a is in denominator. So to find that, we have to search for all the possible valid values of a, values of b. Only then we can find the product. Only then we can find b square by a, and then we can find whether that is in map or not. So a and b square by a, this is not very like this is not very straightforward. So given 3, we cannot try to find all the values which have perfect square, like which have b square by a. This can be simply refactored to other way. What is that? So if we clearly observe 2 8, can we observe anything? So 2 8 is simply 2 and 2 into 4, right? So 4 is perfect square. So from this what we got? So we got that any number, let's assume that it is a, and any other number which is kind of a into x square. So if we have a number a and if there is any other number which is like a into x square, then these both will always be a good pair, must be a good pair, because both have a and we are multiplying this both and we already have perfect square in this. So product will always surely be a perfect square. So if we have a number x and if we have some kind of number x square, we got a good pair. A can be prime or anything. So a can be 2 and it can be 2x square. So x can be 1, x can be 2, 3, 4, 5 and so on. So independent of x, these both products will be perfect square. Why? Because we have same number multiplied and we have other perfect square. So this is the only possible case. So is there any possible case where a and non-number, like not a number which is like a square? That is not possible, because if this is a, this must be some kind of x square. Else how it is perfect square, right? So this is the only possible case. So from this what we got? So is there any common thing between a and ax square? Is there any common thing? If we clearly observe, yes. What if a is prime? Let's assume firstly, let's say is prime. So if a is equal to prime, a is equal to a, and ax square, can this be turned to a? Can this be stored as a? Because ax square and a is valid, this pair is valid. So what if we try to store some kind of map of square free value? What is square free value? If we have ax square, we will try to boil down this to ultimate value where that cannot be divided by perfect squares anymore. And if we try to store that value in the map, then by hash map we can get whether numbers are square free or not. Like for example, let's say we have 2, 8, 6, 6, 4. So we have this array. And coming to 2. So can we divide 2 by any other perfect square where we can boil down this? No, because 2 is the least prime value. So map of 2 is equal to 1. And now let's come to it. So coming to it. So let's start dividing by, so we'll check all the values till square root of 8. So we'll come to 2. So is 2 and 2. So because we are dividing perfect square. So check if 2 and 2 is divisible by 8. Is that divisible? Yes. So simply divide by 2. Divide by 4. What is the value you get? We get 2. And can we boil down 2 by another value? No. So increase the value to 2. So this means that both 2 and 8 have same square free value, which is 2. So this means that these two are good values. These two is a good pair because 2 into 8 is 16, which is a perfect square. And then come to 6. So coming to 6, can we divide by 2 into 2? No. Can we divide by 3 into 3? No. So we reached all the prime values. So we cannot do anything. So simply store 6 of 1. And then coming to 6 again. So coming to 6. So 6 cannot be divided. So simply make 6. So both values in the map of 6 are perfect square because product is perfect square. So this is a good pair. So for example, MP of P, if there are 3 numbers, it means that we got 3 pairs. We got 3 C2 pairs which are good. And similarly, let's come to 4. So coming to 4, is 2 on 2 divisible by 4? Yes. So simply divide, what is the value you get? So 1. Is there 1 already? No. So add 1 to 1. So in this way, if we try to store ultimate boiled down perfect square free value, then whenever we have an index egg. So now let's say we got 28644 and then we stored the values, square free values in the map, right? So 22 and 61 and then 62 and 11. So we got this. And now let's say we got index 2. So we have q queries and we got index 2. So whenever we are at index 2, we have to find all the numbers which have perfect square 1 multiplied with this. So now no need to find brute force because we already have this. So now we can find square free value of 6. So square free value of 6, which is 2. Sorry, which is 6. And now we'll find in the map. So the total number of values minus 1 is the total number of pairs we can get with 6 because these 6 are all included. So simply subtract 1. So 1 pair. So there is one other number where product of that number into this number is a perfect square. So in this way we can try to find the answer very simply in an array. How? We can try to find the square free values. So how to check the square free values? Let's check just the part of this code. So for every index, so ultimately we don't need the original value. So we want the ultimate value boiled down from the original value. So start for all integers and store this in the value. Like x is the temporary value, which is initial value, and then start traversing from 2 to square root of x. Why only till root of x? Because this can be the only maximum value where we can check whether root x into root x is divisible. If this is more than root x, there is it does not make sense. For example, if we are at 10, so okay, should we check whether 4 into 4 is divisible? 10 is divisible by 4 into 4? No, because it is more than 10. So this will not be surely divisible. So it is better to check till root of x. So j2 root of x, then find if this is 0. Find if the modulo j and j is 0. If that is the case, then divide. And then loop the whole till whole values. And finally, make square free of I is equal to x. So we are changing the given value to square root of I. So in future, anytime if we want the value of I, we can simply access square root of f because that is the ultimate square free value of that index. So now we got how to do for array. So let's take some example for 120. That is the ultimate value because we'll check for 2. 2 into 2 is divisible. So simply divide by 4. We'll get 30. So 30 is 2 into 3 into 5, which is not a product of any perfect squares. So this is the ultimate value. And coming to 500, so divide by 2. Yes. So after dividing by 2, we will get 125. So can we divide by 3? No. Can we divide by 5? Yes. So after that, we will get 5, which is ultimate value for this. So now we got the answer. And now, let's say we are a tree. So when we are a tree, let's assume that we are at node x. When we are node x. So when we are at node x, we have to find the ancestors with same square free value as x, right? So this is exactly same as array, but instead of whole array, we have to find in the ancestors whether there is the same value of x or not. So what can you get from this? Whenever we are at node A, we want the answer, like we want already computed values for parent. So start DFS. So start DFS from node 0, do DFS for 0, and then come to parent, come to child, and then do DFS and find the answer. Go to children and find the answer and from. So let's just do take just snippet. So what we want in the DFS. So into node, which node we are at, into parent we can maintain, but here we are just maintaining u and v, not uv and vu. So you can maintain parent also. So for now, let's assume that we are not maintaining parent. So we are just using node, and then we want the adjacency list. So this is the adjacency list, and also now we want, for example, we are at node u, and we want all the pairs, right? For example, this node value has square free 2, this node has 3, this node has 6, and this node has 3, present node has 3. So without storing square free values of all the ancestors, how to find how many are there with same square free as this? We have to traverse again, which is more than often. So whenever we are at index I, we have to store some hash map in the DFS also, saying that square free value of node 2 has 3 values. So we have 3 nodes with 2 square free value. So you have to have some kind of this map. So 3 is 1, 6 is 0. So in this way, if we have this at any node, we can check square free of present value and we can get from the map, and then we can increment the answer. So without storing the map, how can we get the answer? So we have to get other hash map also, which is saying that map of some square free value is the number of nodes with that square free value. And now when we reach index node, when we reach node, what are the number of ancestors with same square free? It is very simply square free of node of map. So map of this. So this is the number of node, because we did not add MP of, like we did not add this node to the map. So for example, we are at this and hash map hash 2. It means that there are 2 other ancestors. This is not included in the map yet. So we got 2 other ancestors. So simply add to the answer 2. And then now increment the answer, increment in the map. And then very simply to DFS and finally return, like we can return the answer in the main function. But is this correct? Let's do it right. For example, let's say we have 2, 2, 3, 3 and 3. Let's say these are the square free values. And now let's start DFS from 2. So DFS at 2. So is there any map before? No. So simply add 2 and 1 in the map. No increment in the answer, because we did not encode any pair yet. And now let's start DFS. So we came to DFS at 2. So 2 and 2. So is there any other one before? Yes. So increment the answer. And now increment which is 2 now. Like increment, because we got other node which with square value 2. So increment in the map. So now 2 2. Because there are 2 nodes with square value 2. And now we are using DFS, right? So we are in this node. Undo DFS for this. So 3. Is there any other node with 3? No. So simply add 3 to the map. And then return to 2 again. So we return 2 again. Very good. And now we came to other child also. Coming to 3. So is there 3 already? Yes. So simply increase the answer, because 3 already there, and increment the answer. And now these all are completed. Come 3 again. So we got 2 other already. So simply add 2 and make this 3. So total answer is 4. So is this correct? This is absolutely wrong, because if we clearly observe, we are forgetting that we are checking only ancestors, right? So let's say we done the DFS for this node. Let's say we done DFS for this node. So after DFS, what is the ancestor map containing? 2 2, because 2 nodes with square free value 3 and 1 node with square free value 3. So we completed this, and now we came to this node again. So whenever we are reaching this node again, we have to remove this from the map, right? Because like we completed the DFS for the child node and we are going to child node of other node. So when we are going to child node of other, when we are going to other child node, this is no longer ancestor. This is other sister or brother sibling, but not the ancestor. So when we are completing the DFS of a node, we have to remove the square root value of that node from the map. Else it will wrongly assume that this is the ancestor of every other node, right? Because we done DFS for this, so we got 3 and 1. But DFS is completed for this one, so we have to remove this also. Else, when we are reaching this, there is 3 in the 1, so we'll increase 1, which is wrong. So when we complete the DFS, so simply remove the square free value which we had now. Only then it is correct for 3. So hope you got this. Let's take other dry run if it is anything is unclear. So let's say we got 2 2 2 and 3 3. So we done DFS for this. So 2 and 1. And we done DFS for this. We got 2 2. And then we done DFS for this. So we got a 3 1. And now DFS for this is completed because there are no more child nodes. So this is completed. So we'll come to this node again. And in this what we are doing, we'll going like we are looping child wise. So this is completed. So do DFS for this one. So while doing DFS for this one, we are checking whether 3 is there or not. Here it is there, but is this 3, like is this is really ancestor of this? No. So why we are getting wrong here? Because after DFS of this, we are not removing this in the map. So after completion of DFS, minus minus 3 also. So we'll minus minus 3. And then coming to 3. Is 3 already there? No. So simply add 3. And now we complete DFS for this also. So simply remove this also. And now DFS is completed for this also. So simply decrease the value. So 2 is 1. So when we are reaching this, only 2 is 1. Why? Because 2 is the only ancestor. So even these are incorporated, but these are deleted as soon as DFS is completed. And now 2 is 1, which is simply of this. So after doing DFS, simply decrease the square free value. So let's check the code. This is simply updating the square free values and then I'll update the adjacency list. So adjacency of u dot pushback v. So this is undirected, so no need to maintain 2. If we maintain both, we have to maintain parent also. But here I am just maintaining u to v and start DFS from 0. And initially map is empty because there is no values with ancestors or there is no nodes itself. So start DFS and find the square free value, do DFS and decrease the square free value. If you have a doubts, comment below. See you in the next video.